Welcome to the deep dive. Today we're plunging straight into something absolutely fundamental, the incredible, essential world of your body's fluids and how they circulate. I mean, think about it. The very fact that we're alive and functioning hinges on these unseen, intricate networks within us.
And as always, this isn't just speculation. We've got a solid stack of information here, our guide for navigating this vital system. Our goal is to extract the core understanding, the truly fascinating aspects, and present it to you in a way that's both informative and, well, genuinely captivating.
Exactly. Because let's be honest, sometimes when you think about what's going on inside you, it can feel like you need a medical degree to understand it. But what we want to do today is cut through the complexity and highlight those aha moments, giving you, our listener, a really clear and engaging understanding of how your body expertly moves life-sustaining substances around and efficiently deals with waste. So let's get right to it.
It's quite astonishing when you consider the evolutionary journey. Think back to the simplest multicellular life, like sponges or those, delicate coelenterates. They rely entirely on the surrounding water to bring them what they need and take away waste.
Right.
Basically using diffusion through their body cavities.
Right.
But as life became more complex, that simple approach just couldn't keep up.
Right. A jellyfish floating by can manage with the ocean around it. But a dynamic, active organism like, us, needs a far more sophisticated internal delivery and removal system.
Definitely.
And that's where these specialized fluids like blood and lymph emerged a real evolutionary breakthrough, wasn't it?
Precisely. And arguably, the star of this internal network is blood. It's far more than just a simple liquid. It's a specialized connective tissue, a dynamic environment all its own. We're talking about plasma, which is the fluid part, and then what we call the formed elements.
Okay.
Those are the various cells and cell fragments suspended within that plasma. It's a pretty consistent ratio, roughly 55% plasma and 45% formed elements.
Okay, let's dive into this plasma first. You mentioned it's the fluid base. What exactly makes it up?
Picture a slightly straw-colored, somewhat thick liquid that's plasma, and it's mostly water, around 90 to 92%.
Wow, mostly water.
Yeah, but that remaining 8 to 10% is absolutely critical. It's packed with essential proteins. Fibrinogen, globulins, and albumins are the main ones, making up about 6 to 8% of the total plasma volume.
Fibrinogen, globulins, albumins. Those sound like they have key roles. What do they each handle?
I do indeed. Fibrinogen is vital for blood clotting, that life-saving process we'll get into later.
Okay.
Globulins are primarily involved in our body's defense mechanisms, acting as antibodies to help us fight off infections. And albumins, they are key players in maintaining the osmotic balance of our blood.
Osmotic balance.
Yeah, ensuring that fluids don't leak out of our blood vessels inappropriately. They're kind of like the pressure regulators of our circulatory system.
So they're like the repair crew, the security force, and the pressure control all in one fluid. What else is circulating in this plasma?
Oh, a whole range of other crucial substances in transit. We're talking about essential minerals like sodium, calcium, magnesium, bicarbonate, and chloride. Then you've got the energy sources and building blocks being transported. Glucose, amino acids, lipids, all being shuttled around to where they're needed. And interestingly, inactive forms of clotting factors are also present in the plasma, ready to be activated when needed.
Right.
Once those clotting factors are removed, what you're left with is called serum.
Ah, serum. I've heard that term from blood tests.
Exactly. So when you get a blood test and the results mention serum levels, it's essentially looking at the composition of your blood without the clotting proteins, giving doctors a clear picture of other substances circulating in your system.
Okay, so that's the fluid part, the plasma. Now let's explore the formed elements. I know you said that's about 45% of our blood. What are we looking at there?
That's the cellular component. Erythrocytes, which are the red blood cells, leukocytes, the white blood cells, and platelets, also known as thrombocytes. Each of these has its own unique and absolutely vital role.
Let's start with the most numerous, the erythrocytes or red blood cells. I always associate them with carrying oxygen.
You're absolutely right. They are the primary carriers of oxygen. In a healthy adult male, you're looking at an astonishing number, around 5 to 5.5 million red blood cells in just a single cubic millimeter of blood.
That's incredible.
And in adults, they are formed in the red bone marrow. What's particularly interesting is their unique structure.
Yeah.
In most mammals, including us, mature red blood cells lack a nucleus.
No nucleus? That seems counterintuitive. Why would they lose their control center?
That's a fascinating trade-off, really. By losing the nucleus, they can pack in significantly more hemoglobin.
Ah, hemoglobin.
That iron-containing protein that gives them their red color. A healthy person has about 12 to 16 grams of hemoglobin in every 100 milliliters of blood. This hemoglobin is what binds to and transports those crucial respiratory gases, oxygen and carbon dioxide.
Okay.
Another remarkable feature is their biconcave shape, kind of like a flattened disc with indentations on both sides.
Right. I've seen pictures.
That unique shape dramatically increases the surface area of each cell, making oxygen and carbon dioxide exchange incredibly efficient, like having more docking bays for those gases.
So they're like tiny, incredibly efficient oxygen delivery vehicles, maximizing their cargo space by ditching the unnecessary baggage, the nucleus.
Pretty much, yeah.
What about their lifespan? They must wear out eventually after all that travel.
They do. Their average lifespan is around 120 days. After that, they're primarily broken down and recycled in the spleen.
The spleen?
Which is often referred to as the graveyard of red blood cells.
Huh, the graveyard. Okay, so that's the red team. Now for the leukocytes, the white blood cells. They're the body's defense force, right?
Precisely. Unlike red blood cells, they lack hemoglobin, which is why they're colorless. They are also nucleated and present in much smaller numbers, typically between 6,000 and 8,000 per cubic millimeter of blood.
Much fewer than the reds.
Much fewer. And generally, they have a shorter lifespan than red blood cells. We can broadly categorize them into granulocytes and agranulocytes based on whether or not they have visible granules in their cytoplasm.
Granulocytes and agranulocytes sounds like different branches of the armed forces. Who are the key players in each?
Okay, so in the granulocyte category, we have neutrophils, eosinophils, and basophils. Neutrophils are the most abundant, making up 60 to 65% of all white blood cells. They are the primary phagocytic cells.
Phagocytic, meaning they eat stuff.
Yeah, they engulf and destroy foreign invaders like bacteria. Eosinophils, which constitute 2 to 3%, play a role in defending against infections and are also involved in allergic reactions.
Okay.
And then you have basophils, the least common at just 0.5 to 1%. They secrete substances like histamine, serotonin, and heparin, which are involved in inflammatory responses.
So neutrophils are the frontline general infantry. Eosinophils are the specialists for certain types of invaders and allergic responses, and basophils are like the chemical warfare unit, kind of.
That's a pretty good analogy, actually.
What about the agranulocytes?
The agranulocytes include lymphocytes and monocytes. Lymphocytes, making up 20 to 25%, are the key players in our adaptive immune responses. They come in two main types, B lymphocytes and T lymphocytes.
B and T cells, right.
Each with highly specialized roles in recognizing and neutralizing specific threats. Monocytes, at 6 to 8%, are also phagocytic, similar to neutrophils, and they can differentiate into macrophages, which are powerful scavengers that clean up cellular debris and fight off infections.
Wow. Given the sheer variety of white blood cells, it certainly suggests that our bodies face a constant barrage of diverse threats.
Absolutely. It's an ongoing battle.
It's truly incredible how many different types of cells are working together in our blood, each with a specific mission. And finally, we have platelets, or thrombocytes. They sound like they're involved in stopping bleeding.
You're absolutely correct. Platelets aren't actually whole cells. They are fragments of larger cells in the bone marrow called megakaryocytes.
Cell fragments. Interesting.
Yeah. They are present in very high numbers, typically between 150,000 and 350,000 per cubic millimeter of blood. Their primary function is to release a variety of substances that are essential for blood coagulation, or clotting.
Clotting, yeah.
If the number of platelets drops too low, it can lead to serious bleeding disorders and excessive blood loss. So they're like the body's rapid response team for damage control, quickly initiating repairs to our blood vessels.
So we have this incredible army of cells and fragments within our blood, all suspended in the plasma. But this blood isn't just a uniform fluid, as we all know. There are different blood types, A, B, O. What's the underlying reason for these differences?
That's a really crucial aspect of blood biology, especially when we consider the implications for blood transfusions.
Right, transfusions.
The two main blood grouping systems that we focus on are the ABO and the RH systems. The ABO grouping is based on the presence or absence of specific antigens called A and B antigens on the surface of our red blood cells.
Antigens on the surface.
Exactly. And in a corresponding way, our plasma contains naturally occurring antibodies against the antigens that we don't have on our own red blood cells. Understanding blood groups is a stark reminder of our biological individuality at a molecular level,
Yeah.
with these tiny surface markers having life or death implications in medical procedures.
Okay, so if someone has type A blood, their red blood cells have A antigens, and their plasma contains anti-B antibodies. Is that right?
Precisely. If you have type B blood, your red blood cells have B antigens, and your plasma contains anti-A antibodies.
Got it.
If you are type AB, your red blood cells have both A and B antigens, but your plasma doesn't contain any natural anti-A or anti-B antibodies.
Yeah.
And if you're type O,
Type O.
your red blood cells have neither A nor B antigens, but your plasma contains both anti-A and anti-B antibodies. This is why careful matching of blood types is absolutely essential for transfusions to prevent a potentially dangerous clumping and destruction of the recipient's red blood cells.
Right. I remember hearing about universal donors and recipients. Where do they fit into this ABO picture?
Okay, so individuals with type O blood are known as universal donors because their red blood cells lack both A and B antigens.
No antigens to react with.
Exactly.
Yeah.
This means that in an emergency, the red blood cells can generally be given to people with any ABO blood type without triggering an antibody reaction in the recipient. Conversely, individuals with type AB blood are the universal recipients because their plasma lacks both anti-A and anti-B antibodies.
So they can take anything.
Pretty much, yeah. Therefore, they can generally receive red blood cells from any ABO blood type without their antibodies attacking the donated cells.
That makes perfect sense. Now, what about the Rh factor? I know that's the positive or negative part of your blood type.
Right. The Rh grouping revolves around the presence or absence of another specific antigen, called the Rh antigen, on the surface of red blood cells. This antigen was first identified in rhesus monkeys, hence the name Rh.
Ah, rhesus monkeys.
Yeah. About 80% of humans have this Rh antigen on their red blood cells and are classified as Rh positive, Rh plus V. Those who do not have this antigen are Rh negative, RHVV.
Okay.
Similar to the ABO system, if an RHV person is exposed to Rh plus V blood, their body can develop specific antibodies against the Rh antigen. This is why Rh matching is also critically important for blood transfusions, especially for individuals who are RHV.
And I recall there being a specific concern about Rh incompatibility during pregnancy. Can you explain that situation?
Yes, it's a very important consideration for the health of the baby. If an RHV mother is carrying an Rh plus V fetus, typically during the first pregnancy, the mother's blood and the fetal blood are usually kept separate by the placenta.
Usually separate, but not always.
Well, there's a possibility that during delivery, some of the fetal Rh plus V blood can enter the mother's circulation. This can cause the mother's immune system to become sensitized and start producing anti-Rh antibodies.
Ah, okay.
In subsequent pregnancies with another Rh plus V fetus, these maternal anti-Rh antibodies can cross the placenta and attack the red blood cells of the fetus, leading to a condition called erythroblastosis fetalis, or hemolytic disease of the newborn.
That sounds quite serious.
It can be very dangerous for the fetus, causing severe anemia and jaundice.
Is there a way to prevent this from happening?
Yes. Thankfully, there is a very effective preventative measure. This condition can usually be prevented by administering Rh antibodies, often called RhoGAM,
Right.
to the RHV mother shortly after the delivery of her first Rh plus VV child. These injected antibodies essentially neutralize any fetal Rh plus VD red blood cells that may have entered the mother's system, preventing her immune system from developing its own long-term anti-Rh antibodies that could harm future Rh plus V pregnancies.
That's a significant relief to know that there is a way to protect future pregnancies. Okay, now let's shift our focus to what happens when we get a cut. You mentioned fibrinogen earlier. How does our blood actually stop flowing and form a clot?
That's the process of blood coagulation, or clotting, a truly vital defense mechanism that prevents us from losing excessive amounts of blood after an injury. What occurs is a complex and carefully orchestrated sequence of reactions. Yes. The end result is the formation of a blood clot, also known as a coagulum, which is essentially a three-dimensional network of protein fibers called fibrin. These fibrin threads trap dead and damaged blood cells, effectively creating a plug that seals the broken blood vessel.
Like that biological net you mentioned earlier.
Exactly. Imagine a series of carefully placed dominoes. An injury knocks over the first few, platelets and tissue damage, which then trigger the next in line, eventually leading to the formation of the fibrin mesh, the final dam that stops the bleeding.
So how does this inactive fibrinogen in the plasma get converted into this tough fibrin meshwork?
That conversion is catalyzed by an enzyme called thrombin. However, thrombin doesn't exist in its active form just floating around in the blood.
Okay.
It is itself formed from another inactive plasma protein called prothrombin. And the conversion of prothrombin into thrombin requires an enzyme complex known as thrombokinase.
Thrombokinase?
Yeah. This thrombokinase is generated through a cascade of linked enzymatic reactions involving various clotting factors that are present in the plasma in their inactive states. It's a chain reaction where one activation leads to the next.
It sounds like a very precise and rapid chain reaction at a molecular level. What sets this whole cascade of events in motion when we get injured?
Injury or trauma to a blood vessel wall triggers platelets in the blood to become activated.
The platelets again.
Yep. These activated platelets undergo a change in shape and release a variety of factors that initiate the coagulation cascade. In addition to platelet activation, the damaged tissues at the site of the injury also release certain substances, often called tissue factors, that contribute to the clotting process.
Okay.
And crucially, calcium ions play an essential role in many of the steps within this coagulation cascade.
Calcium ions too. Interesting. So it's a coordinated effort involving the activated platelets, the damaged tissue-releasing signals, and the plasma proteins all working together, with calcium acting as a key facilitator. It's amazing how all these components interact to stop bleeding. Now, we've talked extensively about blood, but our outline also mentions lymph, or tissue fluid. What is the role of this other fluid in our bodies?
Okay, think of it this way. As blood flows through the incredibly tiny capillaries in our tissues, some of the water and small water-soluble substances present in the plasma are constantly being pushed out into the spaces that exist between our cells.
Leaking out.
Sort of, yeah. This fluid that bathes our cells directly is called interstitial fluid, or tissue fluid. However, the larger proteins and most of the formed elements, like red blood cells, remain within the confines of the blood vessels.
So tissue fluid is essentially blood plasma that has leaked out of the capillaries, but without the big proteins in blood cells. What's its composition?
Its mineral composition is actually quite similar to that of blood plasma. And this tissue fluid serves as the immediate environment for all of our cells, acting as the crucial medium for the exchange of vital substances, nutrients, respiratory gases like oxygen and carbon dioxide, and waste products between the blood circulating in the capillaries and the individual cells.
Right, the middleman between blood and cells. And what happens to this tissue fluid? It doesn't just accumulate in our tissues, does it?
No, it doesn't. We have a remarkably elaborate network of vessels called the lymphatic system that is responsible for collecting this excess tissue fluid from around our body and eventually draining it back into the major veins of our circulatory system, close to the heart.
The lymphatic system.
Once this tissue fluid enters the lymphatic vessels, we give it a new name. We call it lymph.
So lymph is essentially tissue fluid that has entered the lymphatic vessels. What are its main functions?
Besides its crucial role in returning fluid to the bloodstream and maintaining fluid balance in our tissues, lymph plays a very significant role in our immune system.
Ah, immunity again.
Yes, because the lymphatic system is home to a large number of specialized lymphocytes, those key white blood cells we discussed earlier, which are essential for our adaptive immune responses. Lymph also serves as a transport route for certain nutrients, as well as hormones. And interestingly, in the small intestine, fats that we absorb from our diet are transported through specialized lymphatic vessels called lacteals before entering the bloodstream.
Fats travel via lymph first. Huh. So the lymphatic system acts like both a fluid recovery system and a major hub for our immune surveillance. Now let's talk about how all this fluid, both blood and lymph, actually moves around our bodies. Our outline mentions open versus closed circulatory pathways. What's the fundamental difference between these two types of systems?
Okay, the primary distinction lies in whether the blood remains entirely within a closed network of vessels throughout its circulation, or if it at some point flows through open spaces within the body.
Open space.
Yeah. In an open circulatory system, which is found in many invertebrates such as arthropods like insects and mollusks like snails, the heart pumps blood into relatively large vessels, but these vessels then open into large interconnected spaces or body cavities called sinuses.
Sinuses, like in our heads.
No, different kind of sinus. In these body sinuses, the blood directly bathes the tissues and organs before eventually returning to the heart.
That sounds like a much less controlled way for blood to reach the tissues compared to what we have.
It is indeed less regulated. In contrast, annelids like earthworms and all chordates, which includes us vertebrates, possess a closed circulatory system.
Closed system, like ours.
Right. In this type of system, the blood that is pumped by the heart always remains contained within a continuous and interconnected network of blood vessels, arteries, veins, and capillaries. This closed system is generally considered to be more advantageous for larger and more active organisms because it allows for much more precise control over the flow of blood to specific tissues and organs,
Makes sense.
enabling efficient delivery of oxygen and nutrients precisely where they are needed.
A more direct plumbing system allows for better control and higher efficiency. Now, let's talk about the heart itself, the central pump of our closed circulatory system. It's a muscular organ, and in vertebrates, it has chambers. How has the structure of the heart evolved in different groups of animals?
It's a fascinating evolutionary story. In fishes, the heart is relatively simple, consisting of just two chambers, a single atrium and a single ventricle.
Two chambers.
They have what's known as a single circulation. The deoxygenated blood is pumped from the ventricle to the gills, where it picks up oxygen. From the gills, the oxygenated blood then flows directly to the rest of the body before returning to the atrium of the heart. So the blood passes through the heart only once during each complete circuit around the body.
So a single loop. What about amphibians and reptiles? Their circulatory needs are a bit more complex.
They are. Amphibians and most reptiles have a three-chambered heart, consisting of two atria and a single ventricle.
3 chambers, so 2 atria, 1 ventricle.
Correct. They have what's called an incomplete double circulation. The left atrium receives oxygenated blood that has returned from the lungs, or gills and skin in amphibians, while the right atrium receives deoxygenated blood coming back from the rest of the body.
Okay.
Both of these atria then empty into the single ventricle. In this ventricle, some mixing of the oxygenated and deoxygenated blood occurs before it is pumped out to both the lungs and the rest of the body.
So not as efficient as having completely separate pathways for oxygenated and deoxygenated blood. What about birds and mammals, like ourselves?
We, along with crocodiles and birds, have evolved a four-chambered heart, 2 atria and 2 ventricles.
The 4-chambered heart.
This allows for complete double circulation. The oxygenated blood returning from the lungs enters the left atrium and then passes into the left ventricle, which pumps it to the rest of the body. Simultaneously, deoxygenated blood returning from the body enters the right atrium, then passes into the right ventricle, which pumps it to the lungs for oxygenation.
Right.
The crucial aspect here is that there is no mixing of oxygenated and deoxygenated blood within the heart, making this a highly efficient system for delivering oxygen throughout the body. This efficiency is what fuels the higher metabolic rates of birds and mammals like us, enabling our active lifestyles.
Okay, so let's really zoom in on our own remarkable 4-chambered heart. Where is it located within our bodies, and what's its basic anatomical structure?
Our heart, which develops from the mesoderm germ layer during embryonic development, is located in the thoracic cavity, situated between the two lungs and slightly tilted towards the left side of the chest.
To the left, yeah.
It's roughly about the size of your clenched fist. For protection, it's enclosed within a double-layered membranous sac called the pericardium.
Pericardia.
And the space between these two layers is filled with pericardial fluid, which acts as a lubricant to reduce friction as the heart beats. As we've discussed, the heart has 4 chambers. 2 smaller upper chambers, called the atria,
Yeah.
singular, and 2 larger lower chambers, called the ventricles.
And these 4 chambers are kept separate from each other by walls, right?
Yes, they are. A relatively thin muscular wall called the interatrial septum separates the right and left atria. Similarly, a thicker and more muscular wall, the interventricular septum, divides the right and left ventricles.
Thicker between the ventricles makes sense.
Exactly, more pressure there. Additionally, on each side of the heart, the atrium and the ventricle are separated by a layer of thick fibrous tissue called the atrioventricular septum. Within these septa, there are openings that are equipped with valves to ensure that blood flows in only one direction between the chambers on the same side of the heart.
And these openings have those crucial valves, I imagine, to make sure the blood flows in the correct path and doesn't go backward.
Absolutely essential. The opening that connects the right atrium to the right ventricle is guarded by the tricuspid valve.
Tricuspid, 3 flaps.
Which is named for its 3 flaps, or cusps. The opening between the left atrium and the left ventricle is controlled by the bicuspid valve, which has 2 flaps, and is also known as the mitral valve.
Bicuspid or mitral? Okay.
Then at the exits of the ventricles, where the right ventricle pumps blood into the pulmonary artery leading to the lungs, and where the left ventricle pumps blood into the aorta, the body's main artery, we find the semilunar valves.
Semilunar valves.
These valves are designed to ensure that blood flows only from the atria into the ventricles, and from the ventricles into the pulmonary artery or the aorta, effectively preventing any backflow of blood. They're like one-way traffic controllers for the bloodstream.
So they act like one-way doors, ensuring a smooth and unidirectional flow of blood through the heart. What about the muscle tissue that makes up the heart itself? Is it a unique type of muscle?
Yes. The entire heart is composed of a specialized type of muscle tissue called cardiac muscle. Interestingly, the walls of the ventricles are significantly thicker than the walls of the atria.
We mentioned that, yeah.
This difference in thickness reflects the greater force that the ventricles need to generate to pump blood out to the lungs and to the entire rest of the body, compared to the atria, which only need to pump blood into the ventricles. And within the heart muscle, there is also specialized cardiac muscle tissue known as nodal tissue.
Nodal tissue, what's its specific function within the heart?
This nodal tissue has a remarkable and crucial property. It is autoexcitable.
Autoexcitable.
Meaning it has the ability to generate its own electrical impulses or action potentials without requiring any external nerve stimulation. The most important component of this nodal tissue is the sinoatrial node, often abbreviated as SAN.
The SAN node.
Which is located in the upper right corner of the right atrium. The SAN has the highest rate of generating these action potentials, typically around 70 to 75 per minute, and it is responsible for initiating and maintaining the rhythmic contractions of the heart. For this reason, the SAN is known as the heart's natural pacemaker.
Pacemaker.
Right. The rate set by the SAN dictates our normal resting heart rate, which is typically around 70 to 75 beats per minute, averaging about 72.
So the heart has its own built-in electrical system, like a self-winding clock. What other components are part of this nodal conduction system?
We also have the atrioventricular node, or AVN, which is located in the lower left corner of the right atrium near the atrioventricular septum. When the electrical impulse generated by the SAN reaches the AVN, it is briefly delayed.
A slight pause. Why?
That delay is crucial, actually. It allows the atria to fully contract and empty their blood into the ventricles before the ventricles themselves start to contract. From the AVN, a bundle of specialized nodal fibers called the atrioventricular bundle, or AV bundle, also known as the bundle of His, extends through the atrioventricular septum, which is the wall between the atria and ventricles, and then it divides into right and left bundle branches that run along the interventricular septum, the wall between the ventricles. Right. These bundle branches further subdivide into a network of smaller fibers called Purkinje fibers, which spread throughout the entire muscular tissue of the ventricles. This intricate network ensures a coordinated and efficient contraction of all the heart chambers.
Okay, so the SAN fires off the initial signal. It spreads across the atria, gets briefly held up at the AVN for timing, then races down the bundle branches and fans out through the Purkinje fibers to trigger the powerful contraction of the ventricles. It's like a precisely timed electrical wave that coordinates the pumping action.
Exactly.
Now, how does this electrical activity translate into the actual mechanical pumping of blood? That's the cardiac cycle, isn't it?
Exactly. The cardiac cycle is the complete sequence of events that occurs during one heartbeat, involving the cyclical contraction, systole, and relaxation, diastole, of both the atria and the ventricles.
Systole, contraction, diastole, relaxation. Got it.
Right. At a typical heart rate of 72 beats per minute, the entire cardiac cycle lasts approximately 0.8 seconds. It begins with a phase where all four chambers of the heart are relaxed, a stage known as joint diastole.
Joint diastole, all relaxed.
During this time, the tricuspid and bicuspid valves are open, allowing blood to flow passively from the pulmonary veins into the left ventricle and from the vena cava into the right ventricle, passing through the relaxed atria. The semilunar valves, leading to the pulmonary artery and aorta, are closed at this point.
Got it. Everything's in a resting state, and blood is just flowing passively into the ventricles. What's the next step in this 0.8-second cycle?
Next, the SAN fires off an action potential, causing both atria to contract simultaneously. This is atrial systole.
Atria squeeze.
This atrial contraction provides an extra push of blood into the ventricles, increasing their filling by about another 30%. The electrical impulse then travels through the AVN, down the AV bundle, through the bundle branches, and finally into the Purkinje fibers, leading to the contraction of the ventricular muscles. This phase is called ventricular systole.
Ventricles squeeze.
While the ventricles are contracting, the atria are simultaneously relaxing and beginning to refill with blood returning from the veins. This is atrial diastole.
So while the powerful ventricles are squeezing and pumping blood out, the atria are already preparing for the next cycle. What happens to the heart valves during ventricular systole?
As the pressure inside the ventricles rapidly increases due to their contraction, it forces the tricuspid and bicuspid valves to slam shut.
Slam shut, preventing backflow.
Exactly. This prevents any backflow of blood from the ventricles back into the atria. As the ventricular pressure continues to rise and exceeds the pressure in the pulmonary artery on the right side and the aorta on the left side, it forces the semilunar valves to open.
Valves open outwards,
allowing the blood to be forcefully ejected out of the ventricles and into these major arteries.
And then, after this powerful ejection phase, the ventricles relax again.
Yes, that's ventricular diastole. As the ventricles begin to relax, the pressure inside them starts to fall. Once the ventricular pressure drops below the pressure in the pulmonary artery and the aorta, the semilunar valves snap shut.
Snap shut.
Preventing any backflow of blood from these arteries back into the ventricles. As the ventricular pressure continues to decrease, it eventually falls below the pressure in the atria, which have been passively filling with blood returning from the veins. This pressure difference then forces the tricuspid and bicuspid valves to open once again.
Back to the start.
Allowing blood to flow freely from the atria back into the ventricles, and the cycle begins anew. Soon after, the SAN will fire another action potential, and the entire sequence will repeat. It's such a precisely orchestrated dance of electrical signals and pressure changes.
It truly is an amazing and continuous cycle, all in less than a second. I know we often hear about stroke volume and cardiac output. How do these measurements relate to this cardiac cycle?
Okay, so during each cardiac cycle, the amount of blood that is ejected from each ventricle is approximately 70 milliliters. This is known as the stroke volume.
70 milliliters per beat per ventricle.
Right. Now, if you take the stroke volume and multiply it by the heart rate, which is the number of cardiac cycles or heartbeats that occur per minute, you get the cardiac output.
Stroke volume times heart rate.
Exactly. The cardiac output represents the total volume of blood pumped by each ventricle per minute. In a healthy adult at rest, with a heart rate of around 72 beats per minute and a stroke volume of 70 millidoles per beat, the cardiac output averages around 5,000 or 5 liters per minute.
5 liters a minute. That's like pumping your entire blood volume in about a minute.
Pretty much, yeah. And our bodies are incredibly adaptable. They have the ability to adjust both the stroke volume and the heart rate to meet the changing metabolic demands of the body, such as during physical exercise. Athletes, for example, can have much higher cardiac outputs.
That's a phenomenal amount of blood being moved around constantly. You also mentioned heart sounds earlier, those characteristic lub and dub sounds we hear when a doctor uses a stethoscope. What exactly causes those sounds during the cardiac cycle?
Those distinct heart sounds are directly linked to the opening and closing of the heart valves. The first heart sound, often described as lub, occurs at the beginning of ventricular systole.
Lub.
And is primarily caused by the forceful closure of the tricuspid and bicuspid valves as the pressure builds up in the ventricles. The second heart sound, dub, occurs at the beginning of ventricular diastole.
Dub.
And is caused by the sudden closure of the semilunar valves as the pressure in the ventricles drops below the pressure in the pulmonary artery and aorta, preventing backflow.
Lub dub, the sound of valves closing.
Precisely. These sounds, and any unusual sounds or murmurs, can provide valuable clues to healthcare professionals about the functioning and health of the heart valves. So those simple sounds are actually telling doctors a lot about what's going on mechanically inside our hearts.
Absolutely fascinating. Now, another diagnostic tool we often see, especially in medical dramas, is the electrocardiograph, or ECG, sometimes called EKG. What exactly does that measure, and how does it relate to the electrical activity we've been discussing?
The electrocardiograph is a device that records the electrical activity of the heart over a period of time. The recording it produces is called an electrocardiogram, or ECG. It's a non-invasive and very valuable tool for monitoring the electrical signals that control the heart's contractions from the surface of the body.
From the skin's surface.
Yes. A standard ECG typically uses electrodes, or leads, placed on specific points on the wrists, ankles, and chest to detect these electrical signals. The standard setup usually involves 3 limb leads and 6 chest leads, providing a comprehensive view of the heart's electrical activity from different angles. For routine assessments, often just 3 leads are used to get a general overview.
And that tracing shows those characteristic waves, the P wave, the QRS complex, and the T wave. What does each of those represent in terms of the heart's electrical activity?
Okay, the P wave on the ECG represents the electrical depolarization, or excitation, of the atria.
Q wave atrial depolarization.
Right. This electrical event precedes and triggers the mechanical contraction of both atria, atrial systole. The QRS complex is a more prominent set of waves that represents the electrical depolarization of the ventricles,
QRS, ventricular depolarization.
which in turn initiates the forceful contraction of the ventricles, ventricular systole. This ventricular contraction begins shortly after the Q wave. Finally, the T wave on the ECG represents the electrical repolarization of the ventricles.
T wave, ventricular repolarization, back to resting.
Exactly. The return of the ventricular muscle cells to their resting electrical state, preparing them for the next contraction. The end of the T wave marks the end of ventricular systole and the beginning of ventricular diastole.
So each wave on the ECG is a snapshot of a specific electrical event happening in the heart, which directly coordinates the mechanical pumping action.
Precisely. By analyzing the shape, size, and timing of these waves, clinicians can gain crucial insights into the heart's function and identify any potential abnormalities or signs of disease. For instance, you can easily determine the heart rate by counting the number of QRS complexes in a given time interval.
Right.
And deviations from the standard shape or timing of these waves can indicate a variety of cardiac issues, from arrhythmias, like irregular heartbeats, to signs of a heart attack, like myocardial infarction. It's like an electrical blueprint of the heart's activity, revealing its rhythm and any underlying problems.
That's an incredibly useful diagnostic tool. Now let's go back to the concept of double circulation. We briefly touched on it with the four-chambered heart. Can you elaborate on the two distinct circuits involved?
Absolutely. In our double circulatory system, blood flows in a continuous and specific route through a network of blood vessels. Arteries are the vessels that carry blood away from the heart,
The arteries away.
while veins are the vessels that carry blood back to the heart.
Veins back.
These blood vessels, both arteries and veins, are generally composed of three distinct layers. The tunica intima, which is the innermost lining, the tunica media, the middle layer containing smooth muscle and elastic fibers, and the tunica externa, the outermost layer made of connective tissue.
3 layers.
Interestingly, the tunica media, which is responsible for the vessel's ability to constrict and dilate, is typically thinner in veins compared to arteries, because veins don't have to withstand the same high pressures as arteries.
Lower pressure in veins, thinner muscle layer. Okay, so there are these two separate circulatory pathways. What are they specifically, and what is the main purpose of each?
The first is the pulmonary circulation. This circuit involves the movement of deoxygenated blood from the right ventricle of the heart into the pulmonary artery, which then carries it to the lungs.
Right, ventricle to lungs.
In the tiny capillaries within the lungs, carbon dioxide is exchanged for oxygen. The now oxygenated blood then returns to the left atrium of the heart via the pulmonary veins.
Lungs back to left atrium. That's the pulmonary circuit.
Correct. The second circuit is the systemic circulation. This circuit begins with the oxygenated blood being pumped from the left ventricle of the heart into the aorta, which is the largest artery in the body.
Left ventricle to the whole body via the aorta.
Right. The aorta then branches into a network of smaller arteries, which further subdivide into arterioles, and finally into a vast network of capillaries that reach every tissue and organ throughout the body.
Capillaries everywhere.
In these systemic capillaries, oxygen and nutrients are delivered to the cells, while carbon dioxide and other metabolic waste products are picked up from the tissues. This deoxygenated blood then enters venules, which merge into larger veins, eventually leading to the superior and inferior vena cava, the two large veins that empty back into the right atrium of the heart, completing the systemic circuit.
Body back to right atrium. Systemic circuit. So pulmonary is all about gas exchange in the lungs, and systemic is about delivering oxygen and nutrients and removing waste throughout the rest of the body.
You got it.
What about this hepatic portal system our outline mentions? It sounds like a bit of a detour in the systemic route.
It is indeed a specialized part of the systemic circulation. The hepatic portal system is a unique and crucial vascular connection that exists between the digestive tract, specifically the intestines, stomach, spleen, and pancreas, and the liver.
Digestive tract to liver.
Yes. In this system, instead of the blood flowing directly back to the heart after picking up nutrients from the digestive organs, it first travels through the hepatic portal vein to the liver.
Ah, portal vein.
This allows the liver to directly process the nutrients, toxins, and other substances that have been absorbed from the digestive system before they enter the general systemic circulation and reach the rest of the body. It's a clever filtration and processing system.
Like a checkpoint.
Kinda, yeah.
Yeah.
Ensures the liver gets first pass at handling what we absorb.
That's a really efficient way to manage the substances we ingest. And what about the heart muscle itself? We talked about it pumping blood, but how does it get its own supply of oxygen and nutrients?
Good question. Just like any other active tissue in the body, the heart muscle, or myocardium, requires its own dedicated supply of oxygenated blood and nutrients. This is provided by the coronary circulation.
Coronary circulation.
Which is a specialized network of blood vessels,
Yeah.
the coronary arteries and coronary veins that specifically supply blood to and drain blood from the heart muscle itself. The coronary arteries branch off directly from the aorta, just above the aortic valve, ensuring that the heart muscle receives a first supply of oxygenated blood right away.
Okay, so the heart has its own mini circulatory system to keep its powerful muscle working effectively. Now, we know the sand sets the fundamental pace of the heart, but we also know that our heart rate and the force of its contractions can change depending on what we're doing, whether we're resting or exercising. How is this cardiac activity actually regulated?
Right. While the heart has its own intrinsic rhythm set by the autoexcitable nodal tissue, which is why we say it's myogenic, meaning the control originates within the muscle itself, its activity is also carefully regulated and adjusted by the nervous and endocrine systems to meet the body's changing needs.
Nervous and hormonal control.
Exactly. A specialized control center located in the medulla oblongata, which is part of the brainstem, plays a key role in regulating cardiac function through the autonomic nervous system, or ANS.
The autonomic nervous system, that's the one that operates largely without our conscious control with its sympathetic and parasympathetic branches, right?
Exactly. The sympathetic nervous system, often associated with a fight-or-flight response.
Fight or flight. Speeds things up.
Generally, yes. It releases neurotransmitters like norepinephrine and epinephrine. These neurotransmitters increase the heart rate, increase the strength of the ventricular contractions, and consequently lead to an overall increase in cardiac output, preparing the body for activity. On the other hand, the parasympathetic nervous system, often called the rest and digest system.
Rest and digest. Slows things down.
Typically, yes. It primarily releases acetylcholine. This neurotransmitter decreases the heart rate and slows down the conduction of action potentials through the nodal tissue, leading to a decrease in cardiac output, which is more appropriate for resting conditions.
So, sympathetic speeds up, parasympathetic slows down. Makes sense.
And in addition to the nervous system, hormones released by the adrenal medulla, such as adrenaline, epinephrine.
Adrenaline rush.
Yeah, that can also have a stimulatory effect on the heart, increasing both heart rate and the force of contraction, further contributing to an increased cardiac output, especially during stress or excitement. So our brain and hormones can fine-tune the heart's performance, like adjusting the engine of a car based on whether we're idling or speeding down the highway.
That's a great analogy. Finally, our outline touches on some common disorders of the circulatory system. What are some of the main health issues that can arise with this vital system?
Unfortunately, like any complex system, the circulatory system can be susceptible to various problems. One very common disorder is high blood pressure, also known as hypertension.
Hypertension, yeah.
This is defined as a condition where blood pressure is consistently higher than the normal range, which is typically around 120 millimeters of mercury, mmHg, for systolic pressure when the heart contracts, and 80 mmHg for diastolic pressure when the heart relaxes.
120 over 80 is normal.
Generally considered normal, yes. Repeated blood pressure readings of 490 mmHg or higher are generally considered to indicate hypertension. Over time, high blood pressure can put significant strain on the heart and blood vessels, increasing the risk of developing more serious conditions such as heart disease, stroke, and kidney problems.
That's a widespread health concern in many parts of the world. What are some other common circulatory disorders?
Another major category of issues falls under the umbrella of coronary artery disease, or CAD, which is often also referred to as atherosclerosis.
Atherosclerosis, hardening of the arteries.
Kind of. It affects the coronary arteries, the blood vessels that supply oxygenated blood to the heart muscle itself. CAD is primarily caused by the gradual buildup of deposits containing substances like calcium, fats, including cholesterol, and fibrous tissues within the walls of these arteries. This buildup, called plaque
buildup,
narrows the arterial lumen, reducing the flow of blood to the heart muscle. This can lead to a range of problems, including chest pain and, in severe cases, heart attack.
And that reduced blood flow can cause that characteristic chest pain we hear about, right? Angina.
Yes, exactly. A common symptom of insufficient oxygen reaching the heart muscle due to narrowed coronary arteries is angina pectoris, often simply called angina. This typically manifests as episodes of acute chest pain or discomfort.
Chest pain?
That are often triggered by physical exertion or emotional stress and are usually relieved by rest or medication. Angina is more common in middle-aged and elderly individuals and is a significant warning sign of underlying coronary artery disease.
A warning sign. Okay. And the most serious condition related to the heart's pumping ability is heart failure.
Heart failure is a serious and often progressive condition in which the heart muscle becomes weakened or damaged and is no longer able to pump blood effectively enough to meet the body's needs for oxygen and nutrients.
The pump just isn't strong enough.
Essentially, yes. It's sometimes referred to as congestive heart failure because one of the main consequences can be the buildup of fluid or congestion in the lungs and other parts of the body.
Congestive heart failure.
It's important to distinguish heart failure from cardiac arrest, which is the sudden cessation of heart activity.
And heart stops completely.
And a heart attack, which is acute damage to the heart muscle resulting from a sudden blockage of blood supply, usually in a coronary artery. So heart failure is more about the chronic inability of the heart to pump efficiently over time.
Okay, different things. Heart failure, cardiac arrest, heart attack.
Right. All serious but distinct conditions. It serves as a sobering reminder of just how vital a healthy circulatory system is to our overall well-being.
Indeed. It really underscores how crucial this intricate network of fluids and vessels is for sustaining life and health. Understanding its workings kind of empowers us to appreciate the delicate balance within us. Well, hopefully this deep dive into the world of body fluids and circulation has provided you, our listener, with a clearer and more engaging understanding of this remarkable internal system, the constant flow of blood and lymph, the tireless and precisely regulated work of your heart, and the indispensable roles that each component plays in keeping you alive and functioning.
And it truly makes you ponder the evolutionary marvel of it all. Given that the heart possesses this inherent ability to beat autonomously, thanks to the sinoatrial node,
the pacemaker,
what could be the specific evolutionary advantages of having this additional layer of external control from the nervous and hormonal systems? Why not just let the pacemaker run the show entirely?
That's a great question. Why have the extra controls?
Yeah.
Flexibility, adapting to demands.
Exactly. It's a fascinating question that wasn't directly addressed in our sources today, but certainly something worth contemplating further. What's the evolutionary payoff for that extra layer of complexity?
Absolutely something to think about. And as always, this deep dive has really just scratched the surface of a vast and complex field. There's a wealth of additional information within the sources we've drawn from and in countless other research areas just waiting to be explored.
Always matter to learn.
Thank you for joining us on this journey as we took another plunge into the fascinating depths of knowledge.